The earliest known truss system was the rope truss used to strengthen the beams of an Egyptian ship on the Red Sea around 1250 BCE. Until modern engineering developed, no similar structures were recorded. Today, trusses are found everywhere, in seas, cities, mountains, homes, communication towers, and even in space. Assumptions for analysis of trusses. The first assumption, each member is connected at its ends by smooth pin joints. In pin connection, the truss members are free to rotate. The second assumption, all forces and supports applied only at the joints. This assumptions simplify analysis, making forces purely axial. If the truss members are in equilibrium, each member being either in tension or compression, a simple truss is constructed from a basic unit, which consists of three members connected by pins at their ends. This unit forms a rigid triangular element. Different configurations of trusses can be created by adding two additional elements to an existing structure. This process can be repeated to construct larger and more complex trusses. Here are some examples of widely recognized trusses commonly used. An example of bridges is the Pritt bridge. Another example of roofs is gambrel roof. First, we'll discuss the method of joints, a simple and systematic approach for analyzing trusses. The method of joints state that if the truss in equilibrium, all joints must be in equilibrium. Newton's third law indicates that the forces between member and pin are equal and in the opposite direction. If the force is directed away from the joint, the member is in tension. Conversely, if the force is directed toward the joint, the member is in compression. In this demonstration, we assume that all forces acting on the members are in tension. Determine the reactions in the supports A and E and the force in each member of the truss shown. State whether each member in tension or compression. Draw the free body diagram and find the reaction forces using the equations of equilibriums. Starting with the equilibrium equation in the x direction, we find that xa equals 0. Then, taking the moment about point A, we calculate ye equals 200 newtons. Finally, using the equilibrium equation in the y direction, we determine that ya equals 200 newtons. By applying the equation of equilibriums on each joint, we can find all the unknown forces. Usually we start with a joint, which only two forces are unknown. In the truss shown, point A or E is a good choice to start with. We will start with joint E as it has the least forces. At joint E, we analyze the equilibrium. Since all members are equal, the angle beta is 60 degrees. First, recall the trigonometric values for beta. Sine of beta equals 0.887 and cosine of beta equals 0.5. We begin with the direction that has only one unknown. In this case, the equilibrium in the vertical direction gives TED equals negative 231 newtons and TEC equal 115 newtons. Similarly, we consider joint A. The y direction equilibrium gives TAB equals negative 231 newtons. The x direction equilibrium gives TAC equals 115 newtons. At joint B, the y direction equilibrium gives TBC equals 115 newtons and TBD equals negative 173 newtons. At joint D, all forces are solved except for the force in member DC. The equilibrium equation in the y direction yield TDC equals 115 newtons. The equilibrium equation in the x direction confirms that our solution is correct. You can do the calculation by yourself. If we add all the forces, we see that the negative values indicate compression, as we assumed all forces in the members were in tension initially. The diagram shows all forces in the truss members and distinguishes between members in tension and those in compression. As we observe from the analysis, the forces in the truss members are symmetric about a vertical axis passing through joint C. If we had noticed at the beginning that the loads and reactions on the truss are symmetrical, we could have saved time by studying only half of the truss, as the other half is identical. A zero-force member is a component of a truss that, under specific loading conditions, carries no tension or compression. These members are critical for maintaining the stability and shape of the truss without bearing any load. Identifying zero-force members can simplify analysis by reducing the number of elements that need to be considered when calculating the forces within a truss. If there are no forces or reactions at a joint, two scenarios can occur. Two-member joint. If there are only two members connected at the joint, both members are zero-force members. Three-member joint. If three members are connected at the joint and two of them are collinear, the third member must be a zero-force member. Additionally, the forces in the collinear members must be equal in magnitude but opposite in direction. Here are the two cases for zero-force members. In the truss shown, determine all the zero-force members. First, we draw the free body diagram. From the diagram, it is evident that joint F has two members and no external forces or reactions. Consequently, members FF and FE are zero-force members. Additionally, observe that at joint E, member EC is a zero-force member based on the equilibrium condition in the x direction of joint E. As a result, these elements can be eliminated, simplifying the structure. In the truss shown, determine all the zero-force members. First, we draw the free body diagram. From the diagram, it is evident that joint E has three members and no external forces or reactions. Consequently, member ED is a zero-force member.